Hi, myself is Ravinkumar. We are from BLR. So today we're going to discuss about motion control. Um, and here my fellow friends with the team. And our topic for today we selected is transmission selection and motor sizing. So let's go into it. So we'll start into the introduction, the part one. Okay, in introduction, in the realm of the modern industrial automation, high-speed material handling servers as backbone of the production efficiency. This project focus on design and engineering analysis of linear motion positioning system, especially for an automated packaging line. So in this project, what we want to transport is a box weighing up to 10 kilo, set distance of 200 mm with high precision repeatability. So unlike other flow conveyors, this application requires indexing motion profile, which must rapidly accelerate, stop at precise location for packaging operation, such as labeling or filling as type lah. And then, as you see, that is the picture of how the design, the schematic of the automated packaging conveyor system could look like. And then next we will go on objective. So the primary objective of the designs are transmission selection to evaluate and justify the selection of the most appropriate mechanical transmission system to convert rotary motor motion into in linear load motion, balancing factor of speed, precision, cleanliness, and cost. Linear analysis, next is about linear analysis, to perform detailed calculation of the total system inertia, J total reflected back to the motor shaft. This includes accounting for mass of load, the inertia of transmission component, such as pulleys, and the coupling. And then for next part is motion profile and torque calculation. To define a motion profile, velocity over time. That is the main thing. That meets the throughout requirement and calculate the required torques for acceleration, constant velocity, which is friction, and deceleration phase. And the next one will be motor sizing and selection to utilize the calculated torque and inertia data to select a commercial available AC servo motor from the manufacturer catalog that can reliable performance and required motion without exceeding its thermal and mechanical limits. And lastly, about the engineering justification, to provide a robust defense of the design choice, significantly addressing the concept of safety margins, inertia matching for control stability and considerable for future system expansion. That's all from me. So after this, Muhammad Darwis will take on for the task one.
Okay, so my name is Muhammad Darwis bin ROSLAN. My matrix number is B112 102444. Okay, so the first task is about the system definition, and which is basically the system requirements and assumption. So these are the parameters. The first one is a motion type. The value is linear. We require no unit, and the description for this is a horizontal index motion. And the next thing is the total moving mass for these parameters. The value is like uh, 10, and it's in kilograms. It includes like payload box, back section, and carriage. And the travel distance required for this system is 200 millimeters 200 millimeters. And that's the distance between packaging stations. And the move time it took for this system to move is 0.6 second. The duty cycle is continuous with 24/7 operation within dwell times. And the friction coefficient for the system is 0.05. This is the assume for linear guide rails. And the safety margins for this is 50%, and it's applied to all RMS stock for robustness. Okay, next one is the task two, which is transmission mechanism selection. The selected mechanism is tooth timing belt drive. For this packaging application, a tooth timing belt mechanism was selected over other alternatives such as ball screws, rack and pinion, or flat friction belt. So the reason that we choose this system, this belt, this timing belt drive is because of the synchronous precision, unlike flat conveyor belt, which rely on friction and prone to slippage. The timing belt provide more synchronous motion. The tail of the belt mesh positively with the pulley, ensuring that the motor encoder's position directly correlates to the linear position of the load. This allows the high repeatability required for labeling and filling tasks. Next one is the speed and the cost. While uh, a ball screw offers higher force capabilities, it is generally limited in speed over long stroke length due to whipping effects. A timing belt is significantly more cost effective for long travel conveyors and can easily achieve the required speed without any mechanical limitation. So the third one is the cleanliness and the maintenance. A rack and pinion system often require like constant lubrication, which is grease, which can attract dust and contaminate the packaging environments. So this timing belt it runs cleanly and quietly with minimal maintenance, making them ideal for food and beverage or consumers good packaging sectors. The next one is the efficiency. Timing belt usually are highly efficient, typically around 90 to 98%, ensuring that maximum motor power is transferred to the load rather than being lost to friction. So this is the picture of the timing belt, which is the close up of the synchronous timing belt and pulley transmission. Okay, so next one is the task three. I'm gonna pass it to Ravinraj. Thank you for listening.
Okay, my name is RAVINRAJ. I like PRAGASAM. I want to explain about inertia calculation. The objective is calculate the total inertia reflect to the motor shaft and to ensure the selected motor can control the load stability. The system parameter is pulley material aluminium. Its density is 2700 kg. Pulley dimension outer diameter 14 mm. R is 0.007 m. Width L is 15 mm. Load mass is 10 kg. Then motor inertia from the Mitsubishi Electric catalog for the SGKR43 model 400 watt. The J motor equal to 0.371 multiply 10 kg N2. The coupling inertia assumed to standard aluminum coupling 20 mm and L is 30 mm. Then the coupling is pi 0.03 multiply 2700 and 0.02 divide by 32 1.27 multiply 10 negative 6 kg m2. Then after that transmission pulley today treating the pulley as a solid cylinder. Then the pulley is pi LPD4 divide 32. The pulley is pi 0.015 2700 0.014 divide by 32. equal to 1.53 multiplied 10 cos negative 7 kg m2. Reflected load inertia. The linear mass of 10 kg is reflected to the motor shaft based on the pulley radius is 0.007 meter. Then J log is 10 kg multiplied 0.007 into 4.090 multiplied 10 negative 4 kg m2. The total system inertia is the J motor is 0.371 plus J coupling is 0.0127 plus 0.0015 plus 4.90 multiply with 1084. The total J is 5.28 multiply with 10 negative 4 kg. Next page. Then the task 4 is motor sizing analysis, velocity and acceleration calculation based on moving 0.2 meter in 0.6 second. The max linear velocity is 0.2 meter divided by 0.4 second and then minus 0.5 minus. Angular velocity is 0.5 divided by 0.007. The answer is 71.43 radiation.